Hello and welcome to Tattvadeep, Conversations and Explorations. For a fourth episode in physics, we sat down with Professor Rajesh Gopakumar. Professor Gopakumar is a theoretical physicist who is a senior professor and director of the International Center for Theoretical Studies, Tata Institute of Fundamental Research in Bengaluru. His research interests lie in string theory and quantum field theory. He is a recipient of the Birla Science Prize in Physics in 2004, the ICTP Prize, and the Swarnajayanti Fellowship in 2006, and many, many more. He's a founding member of the Global Young Academy and was elected the Fellow of the World Academy of Sciences in 2015. He's also a Fellow of the Indian Academy of Sciences, the Indian National Science Academy, and the National Academy of Sciences, India. In this interview, Professor Gopakumar talks about how our ancestors saw patterns in nature and slowly learned to harness the potential hidden in them. With time and advancement, this pursuit became the domain of physics, from where emerged the theories of the very large, the very small, and the very complex. He also talks about the differences in the way Indians and Westerners approach physics, how a philosophical approach enriches physics, what makes a unified theory interesting and likely to come about, and an underlying interconnectedness that mysteriously binds all theories of physics. We hope this conversation can help the listeners see the tattva, a true essence of physics, and the important role it plays in helping us understand the world we live in and appreciate the fundamental forces that lie underneath everything. Hello and welcome, Professor Gopakumar. Welcome to Tattvadeep, and thanks a lot for joining us today.
You're most welcome. I'm happy to be with you on your channel.
Great. So I'd like to start this conversation by asking you to probably take us down the memory lane, or take us down history by telling us how physicists of the ancient world view physics. How did they view it? And how do people in the modern world, physicists in the modern world, view it? And also, perhaps, if you can tell us how the goal of physics has evolved with time.
Okay. Very appropriate indeed place to start. So physics is, at some point, physics was not differentiated as a subject: physics, chemistry, maths. I think it was part of what in some ways used to be called natural philosophy, the philosophy of nature, understanding what in what way you can perceive and understand the patterns of nature. I think this is probably something in all cultures and civilizations. There has been always a drive to make sense of your surroundings, because there is a great deal of complexity in the world around us, but at the same time, starting with very basic things, you see certain patterns. And I guess the most elementary pattern is the sun rising and setting every day. Then on a longer time scale, the seasons appearing every year. So all cultures had to take notice of this, and they had to actually understand this because, and I think, I mean, though we don't have written history very far back, but certainly from, I think, things that we know about the first settled civilizations, like which started with agriculture and so on, it was very important to know about the seasons, because the crops and their harvesting were tied to the seasons. Now, if you think, where do the seasons come from? They come from the movement. Ultimately, now we know, of course, that they come from the movement of the Earth around the sun and the tilt of the Earth's axis. And so in some ways, I think the origin of physics is tied to the cosmos around us, because in trying to make sense, and people observe the stars, the night sky patterns, and try to make sense of even the motion of the pattern of these stars. There were some objects that people noticed move a little differently from others, and these are what we now know as planets, and so on. And this was important This was again very important for navigation and for people, the seafaring civilizations, and as a way to sort of understand understand how you might find your way in when you're migrating from one part of the world to another. So I think in a way it's quite appropriate that the origin of physics is tied with this, with our deep connection to the cosmos, and of course as civilization developed and people realized they could try to measure these patterns. So they measured the length of the day, the length of the year, and you have different years, the phases of the moon, and so on. And you could measure these, and you found patterns that the moon, it's roughly about 28 days, and then it recurs, and then there is a yearly pattern. And people needed to measure the length of the year very carefully. At the same time, the science of geometry arose, where people needed to measure things on Earth, the land, and how the first records are of land transactions, and for that you develop the notion of geometry, which we learn in school, areas of rectangles, circles, etc. So in fact, the science of the mathematics of geometry started getting closely connected with the science of astronomy, and you started looking at the stars and trying to measure their altitude. So you needed to know about angles and how high something is and how much things move, etc. So so astronomy and geometry evolved hand in hand in many of these ancient civilizations, and our first mathematics and first ideas of the universe come from here. Of course, astronomy was also connected to astrology, which was a way of trying to see, in fact, somehow people felt that these distant stars perhaps even control our lives, because they seem to control so much about our everyday existence, the patterns on Earth. Of course, I think would say now that astrology is just a way of trying to see patterns where there were none. But astronomy grew, and we learned a lot. We learned a lot about first the solar system, and gradually people moved from the Earth-centric view of the universe to the solar, that we realized that the strange motions of these planets could all be explained if you thought of all these planets as moving around a single sun. And that was, of course, a major liberating concept, because you realize that the Earth was not the center of the universe, and the sun was, if at all, anything, it was the thing around which, and the Earth was just one planet among several. And I think, this is one of the aspects of science that I personally find very liberating, because it sort of takes you a little bit from your human concerns to something a little much beyond you, and connects you in that sense, and not by and sometimes people feel, oh, but you're not the center of the universe, so you're nothing. But it's not true. It's quite remarkable that we as human beings sitting on this little third rock away from a small, medium-sized sun, which is in the sort of extreme corner of the Milky Way galaxy, we can try to comprehend the whole. So I think, so then I think it was with this, the understanding of the solar system and so on, and of course, understanding motion, that modern physics evolved, the physics that we now know, which grew then from a science which was just trying to make sense of immediate patterns to trying to understand universal laws. And this is where Newton's historic role in physics, I think, really is central, because he realized that the law of gravity, which we are subject to on the earth, which is what makes the apple fall from the tree, or as we say in India, the coconut fall on your head. The same laws apply to the moon going around the earth and the earth going around the sun. So it's the same universal law of gravity, which nowadays is taught in high school, the so-called Newton's law of gravity. So that is another big leap, I think, in our conceptual understanding, because we realize these laws also apply universally. It's the same law of gravity that applies in our solar system, in the Milky Way, in the Andromeda galaxy, to the best of our knowledge so far. So physics also became much more universal in scope, and trying to understand different laws. And of course, people try to figure out other laws of amazing phenomena like electricity, even lightning, and the static electricity that you feel when you rub your sweater against something in winter. You suddenly get a spark and this thing, or you rub two Flintstones against each other, or even a magnet. So these phenomena also people try to understand quantitatively in the language of mathematics. So this, you were asking about the evolution. So gradually, as physics evolved, this trying to make sense of the universe and the patterns and the regularities, it became more mathematical, because the mathematics captured the regularities. Mathematics is a language which allows you to capture in a symbolic sense some of the patterns, the regularities. We started with geometry, but the mathematics is geometry. It has algebra, it has calculus, and all these different areas of mathematics. And mathematics, in a sense, developed hand in hand with physics, and both sort of fed into each other. And physics, the language of physics, is really mathematics. So that allows you to probe more deeply into the universe. And now in the 20th century, we've really probed a vast scale of the universe. We've gone to probably something about 1,000,000 times the size of the Milky Way. We've seen the universe, we've probed the universe at such enormous length scales, and we've probed it to about 1/1000,000th of the size of the atom, of the size of a nucleus of an atom. So we've gone to the very, very small, we've gone to the very, very large, but we've gone not necessarily physically. I mean, we aren't able to physically go and explore these very small and the very large, but through the language of mathematics and through technological ingenuity, we have been able to probe these realms which are so far removed from our everyday experience. So that's one thing we see now in physics, because we are now probing the universe at in a domain where we don't have our day-to-day experience sort of fails us. Things are much stranger, much more different than we can imagine. We can maybe through a telescope see some small things. We can kind of comprehend the moon with our eyes. We can look under a microscope and see some tiny cells, but that's a very small range of the scale of the universe. And modern physics enables you to go much beyond that, as I said, both through the wonderful technological apparatuses we have created, as well as through the language of mathematics, which allows you to talk about, allows you to, in a very, allows you to measure, allows you to come up with measurable ways of describing phenomena at those very small scales.
Wow, that was pretty much history in a nutshell.
Thank you.
Yes, very clear. It created a very clear picture of, like the highlights of the last 2000, much, I don't know, how many years would it be?
Yeah, recorded
Century?
history, maybe 3-4 millennia, but this is probably, I mean, the very earliest humans probably have been looking at the sky and looking at some of these patterns even before, but let's say 4,000 or 5,000 years. Yeah.
Great. So now the second part of the question, I think I'd like to elaborate on it a little bit, but it stays essentially the same, which was the goal of physics. So now it seems when it started, when it was, now that we've become settlers and it's all about agriculture, and there's a whole story behind how it all came about, but sticking to physics for now. So there is measurement, there is pattern, there is our dependency on that pattern, there is us trying to harness, the potential of the pattern. All of these things are there. So it's so immediate. Like if I'm a farmer and you're my neighbor, you're a farmer. So physics then is a thing you do at home, like without calling it physics, right? So it was so close to us. So yeah. So now from there, we have come to Sir Isaac Newton. We have long ways away from where we started. We came to Mr. Einstein. We've come to now where we are, where modern physics has taken us today. So now, would you say that this where we are today was the only eventuality for physics? Or would you say that it is the people who became physicists, because we bring in our own sense of understanding, we have our aspirations, we have our ambitions, and we are locked up inside the tight, rigorous world of physics. I agree. There are rules and laws that you have to follow, but we still, being humans, right? We bring in our own sensibilities. So do you think the path that physics has taken since then, from looking at the quantum world, being able to look at worlds far away from our own, right? That this is where we are today as physics stands, is very much dependent on how the physicists who have carried physics on their back because of them?
No, that's a very thought-provoking question. I would say to some extent I can see where that there is a certain that there was a certain direction in which things evolved because of a number of factors. One is of course the fact that we were trying to understand certain patterns for our immediate use. So technology often drives a lot of science, and at the same time, science is also a collective venture, and so there have been many different sort of directions in which science has pushed, but some directions perhaps you could make progress more easily for whatever reason. You could make conceptual breakthroughs and you deepened your knowledge in those areas. So the very, very small that we talked about, this quantum world and the very large cosmos, in some ways that was driven by, so towards the very, very small, by trying to understand the nature of substances, chemistry, and chemistry boiled down to atoms. And a lot of chemistry is about trying to use the transformation of the chemical reactions that you see, starting from cooking to a daily, I mean, in what you have in plants and animals and so on, the metabolic reactions, trying to understand those the chemistry behind them led to one line of development. The astronomy and other things that I said led to this other line of development towards the very large. But there is another frontier which physicists, I think, have not made that much headway into, which is sort of the very complex. And so in some ways it has been easier to make progress towards the very small and the very large, but complex systems which surround us, like the weather, the climate around us, the physics of living organisms, what makes us, how from single cells we become these very complex differentiated organisms, and which in the end even have emergent properties like consciousness and so on. These are questions which I think lie within the purview of physics, but I think physicists have not yet managed to make headway into them. It could be because of historical reasons. It could be because they are intrinsically very challenging questions where we have not developed the conceptual apparatus needed, or the right patterns we haven't deciphered in them. So to that extent, what you say is true, in the sense that there is this whole frontier of things, and it's not just about animate things. Like I said, it's about the weather, and there are these things called chaotic systems. There are complex systems which show very relatively simple systems which actually show complex behavior, and these are things I think people have begun to just, in the last 50 years, I think, begun to explore. But I think we are very far from understanding that. So there are definitely these many unexplored worlds even within physics, but one of the things I've noticed in my experience as a scientist has been that somehow there's a interconnectedness between the different theories of physics. Like even the theories of the very large and the very small have ultimately something to do with each other, and similarly, I think in the complex also, some of the things that we've learned there's a web of connections within the theories that we have of physics, which is also very quite mysterious, and I hope we'll get more insight into that as we go ahead. Yeah.
And do you think that first of all, very wonderfully explained, Professor. This was very interesting. So now the question that comes to mind is, so there are these certain frontiers that physics has not yet broken through, and there are complex systems. I have spoken to physicists, and as a non-expert, someone who's not in the lab going and doing physics day in and day out, I rely on films that kind of break down these ideas, but I don't rely on them on face value. They inspire you to think. So there are certain films, like one of the best films that I remember is Jurassic Park, the Steven Spielberg, the first one, which brought chaos theory, I think, to public consciousness, for the lack of a better word, right? So yeah, the complexity in those systems is, you need just a little bit of thinking to understand what you're saying. It's true, it's complex, I understand. But do you also think that because there is at some point, and if I'm not wrong, maybe in the age of enlightenment, or maybe a little after that, when there was this break of science from philosophy, that because the whole beginning of physics, as we were talking, came about because we started to see, so observation, and we started to then think, so thought, so brain, so mind, and then application, and how to use it, and maybe there were trials and errors and all of that. So like life itself was a lab, right? And your mind was the tool, the technology that you had to work that lab, right? So now at some point when this philosophy kind of got separated, so then the direction of physics became, I don't know, you can't call it misled or anything. It has got us so far that we can speak today like this, being in different places. But somewhere the fact that we could not break through these frontiers, the complex frontiers, is because we're philosophically challenged. Could you say that this break has led to this kind of a distancing from these frontiers?
I can again, I see, I think what you're getting at, and there is, I think, physics would definitely be enriched, or at least individual physicists would be enriched, I think, by engaging a little more with philosophy in some sense, because in a way, what has been historically, I think what had happened was that many questions which fell under the domain of philosophy got transferred to physics, because you learned and you made them more precise, and physics then was able, I mean, even many philosophers asked about the why do things move and what happens and so on. But then after some point, the ideas of motion and so on got made more precise in philosophy. So things moved from philosophy in some sense to a more quantitative physics. But at the same time, I think when physicists were faced with more challenging conceptual revolutions, like in the quantum theory, they felt they needed a certain different approach, a more philosophical approach to try to make sense of that. I wouldn't say it had succeeded, but it certainly helped to throw up the kind of limitations in our way of thinking. I think there are you will find two categories of working scientists or physicists. One set who are very pragmatic, who know that there is a certain framework within which physicists ask questions. It's very well defined in a certain mathematical sense, and you can measure certain things, and you say that, well, that's all I know, and that's enough for me. I mean, whereas there is and you say that other things, they are sort of just talk. I mean, it's not precise enough for me to sort of have a opinion on, or a idea about.
Consider, yeah.
It's perhaps a little limiting, at least from my personal prejudice. I lean a little towards the second category, which tries to see a little more the broader context in which physical theories are embedded as part of a human understanding of nature. And it's true that we are trying to make sense of things ultimately. I mean, what does making sense of something mean? It means trying to have multiple ways of looking at it, understanding it. Maybe it's through mathematics is definitely one tool, but one way to understand it. It's unfortunate that it's a tool that requires sort of specialized knowledge or specialized training in. But I think mathematics need not be the only way to think about certain things. I think sometimes it helps to have some complementary views which kind of flesh out that mathematics. It may be asking too much in some cases, but I think it's worthwhile to make that effort. But I want to actually point to one example in the 20th century of a physicist who thought philosophically and made a major impact in science, which was Erwin Schrödinger, who came up with the idea, one of the founders of quantum mechanics, the Schrödinger equation, and so on. But he gave a set of lectures which was a little more philosophical, called What is Life? A subject very far from his expertise and everything. But he approached it in a certain philosophical way and concluded from very general grounds that the information of life must be encoded in complex crystalline structures. So he kind of made a leap before. This was what actually influenced a lot of biologists to go and look for DNA. The fact that DNA is what captures the genetic information of life was something I think he arrived at more or less from a philosophical physics and philosophy kind of a point of view. How can you have something which is transmitted with reasonable fidelity and at the same time is compact? And he said there must be certain molecules which must be doing this, and these must be, he gave enough clues as to what it might be, and then people like Watson and Crick and their collaborators, they came up with they could isolate the DNA and find the molecule that it was. So Rosalind Franklin, I should say, she's a person who is less acknowledged compared to Watson and Crick, but who had played a very key role in the deciphering of the DNA. So so sometimes it's so there were physicists who that philosophical thinking helped to unravel, in this case, a very complex phenomenon, that namely how DNA encode a lot of the information of life. So there is, I think, a lot of room there.
And it's amazing to hear these exchanges, as you were pointing towards right in the first answer that you gave us, how it's a collective effort. So does this need to find, this desire to find, this want, the willingness to find where we are, the setting that we are in, who we are, what we are made of, where we are, all these are philosophical questions. But I think then physics is also trying to look at it. So it is one lens, then chemistry is trying to, it is another lens, and then biology is that these disciplines are kind of also sharing their ideas directly, indirectly. Now in the world of internet, it's much more, it's easier to have these ideas shared. We had a mathematician on in the first series who was doing mathematical biology. So she's studying how plaque it develops and how it grows, and how being a mathematician, she's brought in her expertise, and what it is helping biologists is cut down the amount of time needed to study what's going on. So it's so, everything seems to be interdisciplinary, and this is a beautiful revelation that we are working collectively, whether we know it or not, because it's the same thing that we are trying to study: life itself, reality itself, ourselves. So I'm sure psychology plays a role, philosophy of course plays a role, right?
I think because nature doesn't believe in these compartments which academic departments and universities have. Nature is nature, and it's what it is. And the more we kind of have some preconceptions of what the world should be, I think that limits our understanding. That so that narrows our perspective. So it's better not to remove these preconceptions that we should be looking at it as a physicist. You should just be free to look at it with whatever tools humanity has come up with, whether through mathematics and computer science. Actually, the 20th century, one of the major, this thing was about the computational approach to both to mathematics and increasingly to even physical problems, that what came up with the works of Alan Turing and so on gives a very new way to think of the world through the language of information and computation. And so these are also valuable tools to understand different lenses through which to view things by. So I like at ICTS, the institute I'm at, we are trying to create a certain atmosphere where people can talk without these boundaries of academic disciplines really coming in the way, and just at the level of ideas.
More power to that, Professor. That is very nice to know. That is very nice to know. And another question that's from what I can hear, what you're saying, another question came up. Can you distill to the best possible way you can an Indian way of looking at, say, physics and a Western way of looking at physics?
Right. I think there is, of course, a very large common ground, and
Sure.
everyone has a certain basic commonality of the conceptual thinking.
Right.
But I think the way of doing science is often a little different, and the way in which you even approach problems can be somewhat different. I think, and that sometimes a cultural aspect shows up there. I think in the way individual scientists sort of mold themselves or see themselves. Certain cultures emphasize certain things, and the physics that's done often has that has a trace of that left in it. Whereas in India, I think I've noticed at least this thing that was mentioned, maybe there's at least amongst the young students who come into the sciences and so on in India, I think a lot of young people come into sciences with this broader philosophical approach and trying to make sense. They come to physics through philosophy and trying to understand nature with the sense of which I think has been a strain in Indian culture throughout, whereas perhaps in the United States, people come to physics because it's very cool. It tells you, it has a lot of interesting ideas, and or they of people who in the US, there's very much a culture of making things and doing things with your hands and with workshops. And so even through childhood, many people make new things, they invent things, which is not so much there in India because of various cultural as well as economic reasons. So I think that lends a different color then to the way in which students come to the subject. And I think that there is at some level an imprint of this, and I would say also broadly the sociology also in India. Maybe we are we think it's important to focus on these big questions, and not so maybe it's changing these days, but it's not so much about what will be the return on this, or what is going to be the benefit to us. I think people feel the need to look at these things. I think it's whereas in many other countries, physics is often perceived as something which will lead to some immediate applications and therefore profits and so on. So you tend to look at things differently. So in some of these aspects, so I think this is where I see cultural things come in. One thing I find interesting is in the pre-independence era in physics, India had some very excellent scientists who made path-breaking contributions, like Jagdish Bose and C.V. Raman and Meghnad Saha and Satyen Bose and so on. And they were inspired by a certain idealism, which I think enabled them, even within the very difficult circumstances, to come to physics but they came to it with a kind of a very fresh mind, and they could therefore make some important contributions, which are lasting contributions to science. So in that sense, I feel there was a certain tradition, which is perhaps now a little less the case. I think maybe there's more globalization and uniformization of attitudes, but definitely I think there was a certain something that was there in the pre-independence era of physicists, which led them to sort of which allowed them to make some very important discoveries, which I think we have not had something comparable post-independence from India. So that's something interesting to think about.
So we're talking about contributions in the field of physics by different physicists from different parts of the world. And then what would you say are some of the biggest questions that physics or physicists have ever asked? And which of these questions that come to your mind now, and even perhaps the answers that we have found to these questions, which of these have shaped the way we think as a race, not only as a community of physicists, but the ones that have had an impact on us? Yes.
Yeah, so again, I think I would go back to the three frontiers of the very small, the very large, and the very complex. And I would say the very large is something now we have a very reasonably good understanding of the way the universe has been evolving as a whole. We believe that it started from a big bang about 14 billion years ago and has gone through several phases, which we now understand fairly well. We have measured things quite a long way almost to the Big Bang itself, and seen in a sense, we have been able to look into the past and see the different aspects of the evolution of the universe. And I think this is has permeated the consciousness of us human beings, as that we are evolving in this universe which is 14 billion years old, and that we are the product of a very remarkable set of events, which has led to the universe being as diverse as it is, and for life to emerge and complex phenomena to emerge. So this picture of the cosmos as a Big Bang, originating in this way, is something which we know for the last 60, 70 years, maybe 100 years at most. But I think it's only in the last 30 years or so that we've been able to have much more confidence in it, and we know it now in a very precise way. And this is why, I mean, you even have sitcoms, The Big Bang Theory. So the Big Bang Theory is really like in the consciousness of people. I think so that's something I think has helped. Something that in the future will probably play a role is that we are now discovering all these exoplanets, that there are many other solar systems out there, and hundreds of thousands of them, which have potential Earth-like planets there, and possibly with other intelligent life or of kinds that might have evolved. And maybe there is something that is in store for us, that we suddenly get to know that we are not alone in the universe, that we are perhaps sharing the universe with many other such planets, and that would be a remarkable change in our thinking of the universe. It's like the kind of things I used to read as a child in the science fiction novels, but now in the last 15 years, the satellite Kepler has found so many. It's like you see that the universe is full of these solar systems, and of all kinds. Some have like some have like giant planets, and only some have Earth-like planets, but in other ways. But it seems like we could have multiple places where conditions like on Earth would have prevailed, and therefore we may not be alone. That would be an ultimate sort of kind of what do you call it, a sort of a dampening to our collective ego, that we are not something so special. I mean, we are another set of, and I think some of that is needed, because I think human beings, we have treated the earth in a very shabby way, and this is why we have a lot of our problems also. So something a little more humbling like that, and would probably help us to be more careful about the way we live.
True. There is yes, I think this phrase infinite potentialities or infinite possibilities, I don't know if it is it's a physics term which is permeated public consciousness, but it exists. And then you see that truth is always stranger than fiction. Fine. That we all agree. But fiction is full of amazing stuff. So science fiction, as you were talking about, there is a film in the 90s that came out. It's called Contact. I don't know if you've seen it.
Yeah, I've seen it. Carl Sagan.
Yeah, it was based on a short story written by Carl Sagan.
Story of Carl Sagan, yeah.
Yes, and in that, it's only towards the end that something is revealed. And then what it shows is not just that you found someone. The Jodie Foster's character always had this this intuition that if there's no intelligent life other than us, it's a waste of space, as she used to say. Her dialogue was waste of space. But then the beauty was in how you interact. So you run into something that's so intelligent and older and superior that it can, it welcomed the entity that welcomed her very calmly and was intelligent beyond measure, because it said you should take one step at a time. So I think to learn to say hello before saying, we've done this, but just to say, shake hands and say, yeah, we always felt it, but we did not know. So that then fiction takes you in that direction also. Mostly we see science fiction as only showing parallel universes, multiverses, and Flash Gordons and this and that. But this film also focused on how to create an intelligent life. What if you just freeze? Exactly. What if you just, what if you take a gun and start because you're afraid? You don't know what you're going to do. Yeah, but if you're prepared, let's be respectful. And so that movie kind of teaches people how to say hello.
Absolutely. I think Carl Sagan was amazing that way. He was one of the formative influences actually for me when I was a school child. His series Cosmos played in the Doordarshan at that time, and I remember every Sunday morning just waiting to watch. I think his books and his he has some very nice passages about the similar phenomena that he calls Earth the pale blue dot. That you can see that, and that so that sense of humility in the face of the large cosmos, I think, was something he very nicely managed to and Contact, I think, was capturing that idea. So let's see how it will be. I think science there might be all these, and I hope we'll deal with it with the wisdom that it needs.
And even like just a little a minute longer on the subject of cosmos and the fact that we're talking about interdisciplinary and how we all stand to gain from each other's wisdom, and we all have something to give to the other field, if you remember the opening theme music of Cosmos, the music just captured the largeness, captured the mystery. It just did it without words, a language of its own, and the physics and the music, that just kind of married so well that you were hooked from the get-go. You knew that you were going on to something that you don't know much about, but you'd like to.
Exactly. Vangelis. It was a theme music by this Greek composer Vangelis, which he has this really soaring music that So yeah, no, that's again one of my favorite pieces of soundtrack.
Mine too, mine too. And on Tatvadeep, at some point we will, reach out to musicians and perhaps even music producers to understand, that some of them might be influenced by the work of scientists, because music
Right.
anyway has, and string theory and science. I mean, the terms are similar, they are interchangeable, and wow, it is fascinating even for a non-expert.
Absolutely, yeah, yeah.
Okay, if you can now tell us a little bit about the fundamental laws of nature that physics has been able to discover, and now connecting it to us people, right? Like, if we get to know these fundamental laws, we study them in school, and they kind of they don't seem to have any durable impact. We memorize it. Indians, I know, we just memorize it. We can say it, like parrot it out. But if knowing it now, and depending on how you'll also share, what kind of impact would you hope that knowing that these are the laws that our universe is built on, as far as we know, that are unchallenged as far as we have gone, and what kind of impact would you hope that knowing these laws would have on the regular everyday guy?
Yeah, no, I think the famous physicist Richard Feynman, he was once asked, if you had one piece of information that you wanted to transfer to, suppose like the earth was going to be destroyed today and everything, all civilization was going to collapse or whatever, and you were only allowed to pass one piece of information to something that might appear in the future, or maybe something else, what is that one piece of information? And he chose, and I think it's a very good choice. He said the world is made of atoms.
I know
So I think that's it's actually quite a profound concept, that we are all made of just 93 different kinds of atoms, 93 because they're stable. There are about 110 or 115 if you include unstable atoms as well. But everything, all the complexity is coming from the different combinations of 93 of them. In fact, most of the time it's not even 93. There are maybe 15 or 20 of these atoms which are responsible for most of the things that we see around us. And these atoms are actually made of an even smaller number of different fundamental particles, electrons, and protons are made of things called quarks. So there's maybe about a dozen or so of these, which make up all the matter that we now know of. And so a lot of so it is, this I think is a very striking fact, that because things seem so different, but ultimately everything is made of just these few little things in different combinations. It's like these are the Lego building blocks of nature, and you have just a few pieces, but from that you can build amazing things. But how they, of course, you put them together and they do amazing things afterwards is another story that's also, of course, remarkable and interesting in itself. But string theory and other such fundamental approaches to understanding nature are trying to figure out these different building blocks and their and a kind of ultimate unity of these building blocks. So distilling these 93 atoms to about a dozen quarks and electrons and so on, and even those, seeing the commonalities between those, is there an underlying even deeper unity amongst them? So it would be remarkable if everything could be just understood in terms of a very few, maybe even one entity, ultimate entity. So that quest of physics, I think, is something I feel people can identify in some sense with, and at the same time find it quite remarkable. So, and it's not only the matter, but also their interactions. So something which look so different, like gravity and electricity, or even electricity and magnetism. A magnet looks very different from the electricity that you feel when you kind of get a static little shock from your sweater or from touching a dry thing. So that these two things are actually are somehow manifestations of the same underlying interaction, and that's another very remarkable fact. And what people are trying to see is whether something like electricity and magnetism are related to gravity, which we also feel, but we think of as something totally different from magnetism. We don't connect a magnet and its behavior with the force of gravity, which pulls us down to the earth or keeps the planets in motion. But maybe there is this underlying commonality. So not only in the structure of matter, but also in the nature of the interactions.
So this brings to mind one of Carl Jung's quotes. So he's definitely studied a lot about chaos and order. And one of his quotes was that in chaos, there is an underlying order. And in order, there is something like an underlying chaos. So things seem to contain each other. And something like that. So what on this topic of the grand unified theory, and what I'd like to ask you is this, that do you think that this the idea of a unified theory came about because the discoveries and possibilities that physics was making available to physicists pointed in the direction of such a possibility? Or was it more the physicists who decided that physics must contain some kind of grand unification and then set about in the direction of that goal?
So I think it's more the former, because you saw that electricity, I think the first unification, so to say, was when James Maxwell in the 19th century realized that electricity and magnetism are, while appearing to be very different, are actually two facets of the same force. So, and in a way, he managed to unify them. And that was sort of a big surprise in some ways, and led people to the idea that maybe these things that we think of as different things are really secretly the same, provided we just think of them in the right way. This idea actually lay dormant for a while, but Einstein tried to make sense of it, but didn't really succeed. But what really succeeded was much later, in the second half of the 20th century, when people realized that there's a different kind of interactions which governs how radioactive material behave. It's called the weak interactions. So those and the electromagnetic interactions are also secretly kind of related to each other. So this gave, so like now people felt this can't be just a coincidence. Mm-hmm. There must be something in this line of thinking that must be correct, because maybe once, it could be a coincidence, but then twice you see it happening again, and then you feel that, maybe they are related. And as I was mentioning earlier, even in the structure of matter, you saw this underlying thing, that what appeared to be different atoms, a carbon atom and an oxygen atom, they have very different chemical properties, but ultimately they are made of the same protons and the electrons. It's the very same. You can take a proton from a carbon atom and put it in a oxygen atom, and it won't change anything. The carbons and oxygen will remain the same. So, and similarly with the electrons. So so physicists were, in a sense, pushed to the idea that there is a kind of underlying unity of both matter as well as interactions. And that is what led to this effort. Of course, if it works out, that will be great, and people have a certain conviction, but in the end, it's nature has the final say. if it works out, then you will see the thing. But I think we in the process of trying to understand this, you would anyway discover deeper aspects to these interactions, even if they were for some reason not ultimately the same. So that I think is the sort of thing that drives physicists in this direction.
So even if there is a theory that all physicists agree upon as a Brownian fair theory, it will not be the end of physics.
No, no, that just maybe I think will tell you at a certain level we've understood a certain unity, but there might be even deeper unities, and that maybe that perhaps is only one road in physics. There are the frontiers of physics extend in many directions, like I said, in the complex, in the very large, and so on. So yeah, so it definitely, I don't think people who talk about the end of physics are being very premature.
Yes, okay. And I was reading this book. It's called Why Beauty is Truth. It's by a British mathematician. His name is Ian Stewart. So I'd like to read a quote from this, and I think the question itself will emerge. He said, a statement that lacks a proof. Okay, I'll read it from the beginning. To Euclid, logical proofs were an essential feature of geometry, and proof remains fundamental to the mathematical enterprise. A statement that lacks a proof is viewed with suspicion, however much circumstantial evidence seems to favor it, and however important its implications may be. Physicists, engineers, and astronomers tend to view proofs with disdain as a kind of pedantic appendage because they have an effective substitute, which is observation. So do you agree with what he's saying? And is it so? And then why is it so? Why do physicists view proofs with disdain and value observation more? I mean, it all seems to have started with observation anyway, so.
Right. So it's just it's kind of a different lens of viewing things. I think when a mathematician like Ian Stewart talks about proofs, that's in the classical mathematical sense. Mathematics has now evolved itself a distinctive identity as something which is modeled along what Euclid and so on did, which is you have a set of axioms and then you try to derive the consequences, and you derive it using laws of logic, and you arrive at a proof which is a true statement which follows if you assume the initial axioms to be true. So that's a closed system in itself. It need not have any reference to the real world or to observations or anything. You could prove a set of results about starting from some axioms, what would logically follow from them. And that's important, and I completely respect within that framework how mathematicians, they need to have because they are not trying to connect it with reality necessarily. They are working in this closed logical system. They need to be sure of their deductions, and that's why proof is very important for them. Whereas physicists or others that he mentioned use mathematics as a way to capture reality, and then they may sort of they are in a way interested in physical truth as opposed to mathematical truth. So the physical or nature's truth. Nature's truth is whatever nature has, what nature obeys, and you are trying to use the mathematics to model that truth. And so observations will tell you whether your mathematical way of capturing nature is correct or not. So observation in that sense, that's the way he means it. But physicists, I think, I mean, I think they have a kind of a little complex attitude towards mathematics. I think many of them, especially in the more theoretical areas like mine, are function in some level like mathematicians, but at some level we are not so obsessed with the proof and more with arriving at a true statement. So there's a famous physicist, Russian physicist, Lev Landau, who made a statement that life is too short to prove theorems. So the idea is that you're interested in coming to the truth and not the proof. The proof is useful if as I said, you're working in this logical system, but if you're interested in describing nature, in a sense, physicists are much more impatient. You want to get to what nature is telling you and not worry about whether you've gotten the dotted all the I's and crossed all the T's. But of course, on a day-to-day basis, mathematical, the ability to argue things logically and mathematically is also important for a theoretical physicist to be able to make certain chains of reasoning. I think it's just that the standards of rigor are a little looser in physics than in mathematics.
In the same book, we were talking about truth and we were talking about proofs, but there is also beauty. There's also beauty.
Yes.
So in that, there is another little paragraph I want to read from this book. So Mr. Ian Stewart is saying that Paul Dirac believed that in addition to being mathematical, nature's laws also had to be beautiful. They had to be beautiful. In his mind, beauty and truth were two sides of the same coin, and mathematical beauty gave a strong clue to physical truth. He even went so far as to say he would prefer a beautiful theory to a correct one, and that he valued beauty above simplicity. So your thoughts?
Yeah, actually, Dirac's thinking and so on, I think is very influential for people in our area, string theory, because in some ways we are talking about theories which are not immediately accessible to observation, whose consequences are not immediately checkable by observation. So we are much more guided by mathematical consistency, mathematical elegance and beauty, and the way everything hangs together and the way it sort of all fits together. It's like in a jigsaw puzzle. I mean, you're trying to piece together some things, and if you're trying to piece together a jigsaw puzzle which you don't know what the final picture is going to look like, you have to go more by, does it kind of fit in with this? And you have much less of a idea of where you're getting and going, and so you have to rely on these feelings a lot more. And so I think this sentiment may not be shared by physicists at large, but the one that Dirac, that Ian Stewart mentioned Dirac as having. But I think among string theorists and others, you will find much more this sentiment resonating, and being guided by that. So I personally, in a sense, agree with that. I think a lot of my personal thinking is often guided by similar considerations.
So now all these deep ideas and incredible discoveries that are taking place in the world of physics that you are a part of, you're contributing to, has it made it easy for you, or has it made it difficult for you now to reconcile with the messy real world?
Yeah, the real world is, I think, I think it's definitely more difficult in some ways, in that you realize that within that you have that there's a sort of a world of order in which you are in when you are dealing with the world of physics concepts. And of course, the real world is much more complicated. But I think your physics training gives you an ability to sort of see through some of the complexities and try to identify the core of things. I think you're trained as a scientist to try to remove externalities from the central notion. So there's often in any issue or in any this thing, there's a lot of irrelevant stuff, but the core relevant stuff is often
the heart of it.
The heart of it, to be able to see through to that and to discard what is inessential and keep what is essential. I think that helps you in a way, I think being a physicist helps you also to gives you that perspective, I think, on things, and in general, even when you have setbacks in life or in interactions or whatever, you still have like a certain compass in your head which you can sort of use to guide yourself. So I think that helps.
Beautiful answer. Thank you. Okay, now, have you seen the film 2001: A Space Odyssey?
Yes, a couple of times. Yeah, definitely.
So what do you think was the monolith? What do you think it signified?
I think it was, I mean, it was again a bit like we were discussing earlier with contact and so on. I think trying to, I mean, a very different kind of intelligence trying to make contact with human beings, but at the same time not directly intruding, and but observing, perhaps gently shaping in some ways at critical moments in history, and trying to sort of lead, just like some parent tries to lead a child, but this is sort of much more long distance parenting.
Much older, much wiser.
So, but not in an explicit way. I mean, trying to intervene at points to take you to another level of consciousness or thinking.
Very, very interesting, Professor Gopakumar. So with that we can conclude this conversation, and thank you very much, Professor. This was so much fun, so enlightening, and I had a really great time, and so many relevant, important, interesting points to pick up from what you had to say. So thank you so much for your insights, your time, and the generosity with which you've shared your knowledge with us.
Not at all. And thank you for the very stimulating questions, which helped the conversation to move ahead and allowed us to explore many different topics. And I'm glad, as I said in the email, I'm glad you are doing this, and out of just passion and interest. And I hope there'll be many like-minded people who will view these videos and will sort of help them to think of, at least for a little while, take their minds to a different plane.
Oh, how kind. That's the best hope we can have for this podcast, Professor Gopakumar. Okay, thank you, and wish you all the best with all your work in the future.
Thank you very much, and all the best for your ventures. Okay, bye-bye.
Thank you. Bye-bye.
My conversation with Professor Gopakumar reinforced the value of observation, humility, and courage, and the importance of these values to make new breakthroughs in physics. I especially enjoyed his views on how one's training in physics can improve one's interactions with the uncertainties of the world and life itself. It will be wonderful to know your thoughts on the interview and if it inspired your worldview in any way. Thanks for being here. I will see you soon with another interesting mind demystifying another interesting topic. Until then, take care.